We have Subir with his second talk on quantum matter.
Okay, so as you've seen, there's been some nice complementary lectures by John. We're covering similar topics, and so I'm going to use that to my benefit. So as I motivated yesterday, we are looking at this very basic field theory, where you have fermions which carry some index sigma, which live inside this Fermi surface, and that the size of the Fermi surface is determined by the chemical potential mu. So mu couples to some global U1 charge, usually the electron density. And then we couple this fermion to a gauge field, which is written as A. And the gauge field could be abelian, non-abelian. There's some gauge group which is very different from the global U1 charge that mu couples to. That's the only important thing. And I'm focusing on the two-dimensional case. Okay, so this theory we try to analyze in a 1 over NF expansion. And to just quickly review, we wrote down a low energy field theory for the fluctuations of this Fermi surface. So the first thing you said, we look at some photon propagating in the direction q. And what we found was that it coupled most strongly to fermions in which this direction q was tangent to the Fermi surface. So the Fermi point here, where you had this tangent parallel to q, and also the antiphoton point on the other side. So then you get two species of fermions, psi plus and psi minus, and these disperse linearly in this direction and quadratically in the tangent direction. So that's so you expand the Fermi surface about that point, and you really get a different theory then for each direction of the photon momentum q. So for a fixed direction, you have this very simple looking field theory. You have fermions psi plus and psi minus that disperse linearly in the x direction and quadratically in the y direction. There's a minimal coupling to the photon. This is just the ordinary coupling. There's no gradient terms here because this is the coupling to a sub x because the photon momentum is in direction y. And in the x direction, you have a linear dispersion, and so the coupling is just to the difference of the charges on the two sides. And then this is the Maxwell term, B squared term for the photon. Okay, so skip ahead. And then we did some perturbation theory. I finished my last lecture by showing you that if you computed this photon loop, that the photon self-energy had this dissipative Landau damping term, omega over q, and this was simply a measure of the density of states of fermions to which a photon could create particle-hole pairs. So this is the same process in relativistic field theory. We have a high energy photon, a gamma ray, can decay into electrons and positrons. Here you have a very low energy photon that can create electron-hole pairs right near the Fermi surface. And there's a large density of states of them down to zero energy. Okay, so the next step is to take this overdamped photon here and compute the electron self-energy. This is the same graph that gives you G minus 2 in QED, but now because our photon is damped, and also because of these rather peculiar dispersions near the Fermi surface. Okay, this is the graph. This is the integral you have to compute, and I won't compute it. But what you get at the end then is a self-energy very similar to the kind that John was discussing, where you get omega to the 2/3. Okay, so that omega, and it's also, well, has both real and imaginary parts, and so this is the important point about the self-energy is that this is much larger than the bare frequency dependence, which is just omega, and so the quasi-particle is not well defined. Okay, so that's the one loop 1 over NF correction. This goes back to calculations by Reiser and Patrick Lee in the late 80s. So it's been understood very well. Been there for a while, but we want to think about it to higher orders and really try to understand what the significance of this non-Fermi liquid state is. Okay. So to summarize then, you get this non-Fermi liquid state in which you have this overdamped photon, and then the fermion Green's function disperses linearly in the x direction, quadratically in the y direction, and this non-Fermi liquid damping. Notice that because of this d by d tau, I have left out the omega term. There's an omega term from the d by d tau. You can just throw it out because not as important as the correction. Okay, so what you notice here that this singular term here has a 1 over NF in front of it. And that's really the source of all the problems, because this, if you send NF to infinity first, that would be saying, well, ignore the damping. On the other hand, if you send frequency to 0 first, this is the most important term. So there's an order of limits of frequency going to 0 and NF going to infinity, which actually makes this whole vector NF expansion quite problematic. So I'm going to come back to that in a minute, but first let me try to explain this z equals 3/2. It looks like a rather mysterious number, and it's going to play a very important role in what I'm going to say today, and just came out of some one-loop calculations. But why it's in fact, however, easy to see it from a more robust argument, and it's really something very crucial to everything I'm going to say. So let's go back to my field theory that I began with. Yes?
When you had the calculation of the self-energy for the fermion,
Yeah.
it had its G.
Yeah, I just dropped that out. Okay. There's a G squared in front of it. Sure.
But the reason why I ask is, I mean, so if there was a G squared...
It's not actually, this is strange power, but
Yeah.
go on.
But then, is there an interesting limit you could take where NF goes to infinity, but you also send G squared to infinity, but keep that as a fixed quantity?
Well, here G is dimension full, so there is no analogous to, there's various other dimensional factors. Really, G is, since it's dimension full, should be thought of as infinity at all stages. Or you can rescale it out by appropriate choice of your length scales. So it's very different from C plus 1 dimension. There's no analog of the two parameters. Anyway, so I was going to give you a simple argument for z equals 3/2. So let's take this field theory, and now I just want to do some simple scaling. So what we have seen, the only insight we need from the computation so far is that this bare kinematic term, d by d tau, is really can be thrown out. So let's just throw it out, get rid of it, and make everything equals to 1. And here's my simple action. Now I've rescaled the gauge field to make this coefficient 1, but I've introduced a coupling lambda here, the Yukawa coupling lambda, or the gauge, well, you can think of it as a gauge coupling or Yukawa coupling. So here's a field theory with only one parameter. Everything else can be rescaled to be unity. And now we have to look at its rescaling properties. Okay. So let's go ahead and do that. It's just a simple power counting exercise. So I want to rescale x by a factor of s and y by a factor of square root of s. That's to preserve this, this d by dx and d by dy squared form. And then let me just rescale time by s to the z. And I need to determine what z is. Okay? So once I know this, I want to preserve the kinetic energy of the fermions. And it's just a two-line exercise to figure out. That means that psi should be rescaled this way. I want to preserve the kinetic energy of the photon. Two-line exercise to figure out A should be rescaled this way. And then finally, that just fixes what lambda is. So this is a homework problem I urge you to carry out. It's just arithmetic. You find lambda scales as 3 minus 2z over 4. So what you see is that you have the only possibility of any kind of scale invariant structure with some non-trivial critical behavior is when this is 0, when lambda is scale invariant and you're at the fixed point. So z equals 3/2 is really the only solution in which any kind of perturbative expansion of this field theory will give you a non-trivial state. So it just follows from just the naive power counting. And what's different from the usual arguments, usually you fix z by the requirement that the fermion kinetic energy be invariant. There's a psi dagger d by d tau psi. Now I've thrown that out because I've argued that the bare kinetic energy is not the important term. But now I'm demanding that, so then I have some freedom left over. I'm using that freedom to fix the gauge coupling, be scale invariant, or the Yukawa-like coupling. So it's like a three-body term. If you keep it invariant, you immediately get z equals 3/2. Okay. So then coming back to the structure, now you understand where this 2/3 come from. It's really a consequence of the scale invariant structure of this low energy field theory. I want to come back to the point that this, which I've already mentioned, that there's 1 over NF here, and omega to the 2/3. So the two opposing tendencies which really make this 1 over NF expansion problematic. And I guess I've already said that. So naively, when you do the 1 over NF expansion, what you find, the naive assumption is just count fermion loops. Every time you have a fermion loop, you get a factor of NF. And that's the basis of the vector 1 over NF expansion in all the textbooks. So here, there's a little subtlety. Because there's a 1 over NF in the denominator, if you're doing a loop integral, then for certain loop integrals, you find you can just ignore this term. Those you're happy with. But for some other loop integrals, you can't ignore this term, and because of this term, you get some NFs in the numerator. So then you start getting rather different factors of NF, some from just counting numbers of loops, and others from the infrared singularities of the loop integral itself. So this was first pointed out by Sung-Sik Lee, and he sat down for a simplified version of this theory where he only had the psi minus, ignored the psi minus term, just the psi plus. He looked for what are the graphs for which the loop integrals give you anomalous powers of NF. And his very beautiful result was that those graphs are precisely the planar graphs. So this is a picture from his paper in 2009. Here's this is the fermion line. The double line is the gauge boson, and the dashed line I just put in to emphasize the fermion loops. And what he showed is that for planar graphs like this, you could recast the singular terms in the graph in terms of fermions running on these lines, which sit right on the Fermi surface. So what you notice here is that the gauge boson is written as a double line. Now usually, in the 't Hooft theory, you write the gauge boson as a double line because you think it has two indices. But here, recall I just told you a few minutes ago, you can think of the gauge boson as a particle-hole pair, both near the Fermi surface. And so you should really think of this double line as one particle on the Fermi surface, another particle and the hole on the Fermi surface, but they really can be anywhere. So there's a free sum over the particle and hole indices, and they have very low energy. And that's what contributes to the fact that each closed loop here is actually a particle or hole sitting exactly on the Fermi surface. And so there are extra infrared singularities from the fact that you have a line of zeros in momentum space. And these, quite magically in the end, show you that you still have to sum all planar graphs. So you tried very hard to avoid summing planar graphs by introducing vector fermions. But the problem told you you can't. You still have to sum planar graphs because of these infrared singularities from these particle-hole pairs sitting right on the Fermi surface. In fact, it's worse than that. We showed that if you included both psi plus and psi minus, even this genus expansion of Sung-Sik Lee broke down, and there were even more singular terms. And so at this stage, we don't know what the large flavor limit is. It's still an unsolved problem. So even for NF equals 10,000, I can't predict what the value of any exponent or Green's function is, because we don't even know the set of all the graphs I have to sum. So it's a very difficult problem, which seems to be, even though it's been declared solved many times by many people, and I'm not going to make the same mistake. Okay.
The planar expansion suggests some string theory, but your subsequent observation
Yes.
is this more complicated?
Yeah, but I'm going to fix that in a minute. But for this problem with the vector expansion, so I think well, let me just answer that. So we're trying very hard to avoid using matrices, and we run into all these problems. So at the end of this, I decided, well, let's just do matrices, and we'll come to that. Yeah.
If you keep the temperature fixed,
Yeah.
and non-zero when you take n to infinity, then do these infrared singularities still bother you?
Yeah, it's the same. Temperature frequency will scale the same way. Yes.
So, but if you keep the temperature fixed
Yeah.
and take n to infinity, then can we get away with the naive planar expansion?
No, I don't think so. Well, let's see. I mean, it depends. Assuming temperature is very low, you want to figure out the singularity in temperature, for example.
No, I'm looking at finite temperature. I'm not scaling the temperature to zero as I take n to infinity.
I don't think you can, because you still just get temperature to the power 2/3 over NF over here, And so you will have to put this term in to control your infrared. But,
Only when temperature.
no, you're right. There'll be some Fermi factors from the fermion loops. Yeah, no, you'll be fine. You'll be fine. Other questions? Okay, so then let me just summarize then what we've learned so far for this key problem. All right. So that summarizes what I've said. So this is the problem I've described, and I've told you we've got some kind of non-Fermi liquid state, most likely with z equals 3/2, which is compressible. But if you try to compute anything that anyone can believe, any number, it seems to be very hard to do it. Okay, because John just preceded me and discussed some holographic calculations, I want to talk about yet another model of a strange metal, which will connect up with the kind of things John was saying. Rather than taking a model of just fermions, let's take a mixture of both fermions and bosons. Okay, and just for convenience, I've now coupled the boson to have the opposite gauge charge to the fermions. There's many possible choices here once you have two species of matter, and I'm just taking some very simple choice in some schematic form. And this is natural to do from the point of view of holography, because you'll always get fermions and bosons. There's always, in supersymmetric gauge theories, both fermionic and bosonic matter. There's also gauginos and so on and so forth. So let's just take some simple model with both fermions and bosons and ask whether this can lead to any non-Fermi liquid phases. So now one possibility, of course the bosons can Bose condense and then you get a superfluid, but we don't want any Bose condensates. So, but one possibility, since they have opposite gauge charges, and also they might have some bare attractive interaction, is that the bosons and fermions can form a molecule, a bound state, or a mezzino, or a fermion and boson. So I'm going to call that C, which is a bound state of a boson and a fermion, and this is a gauge neutral object. So now you have two types of fermions floating around. You have the F fermions and the C fermions. And the very naive picture, which actually turns out to be basically correct, is that you can imagine they both form separate Fermi surfaces. So the C fermions can form a Fermi surface, and the F fermions can form a Fermi surface. But there's a simple counting rule, which you just do the most naive kindergarten counting. Luttinger's theorem ensures that you get the right answer, even for this strongly interacting problem. So naively, you would say, for every boson, there's a C fermion, because every boson is eaten up by an F to form a C. Since the boson can't Bose condense, they must attract an F and form a C. So the number of C's is equal to the number of B's. So the area enclosed by the C Fermi surface should equal the number of bosons. And that's in fact an exact statement to all orders. Then what's left over? How many F's are left over? Well, some of the F's got eaten by the B's. So how many F's are left over? Well, that's Q minus QB, because you took away a number of F equal to the number of bosons. And so the remaining F's that are left over will form their own Fermi surface. Then you just ask about gauge charges. Well, the F's have a gauge charge, and that's what this shady thing is supposed to represent. This glow represents lots of low energy excitation and non-Fermi liquid behavior, whereas naively the C's don't have a gauge charge, and so they should form a relatively sharp Fermi liquid like Fermi surface. Okay, so this is the phase. This is another more complicated strange metal phase that we call the fractionalized Fermi liquid. So it's kind of this dual nature. There's part of it that's fractionalized, and there's a part of it looks almost like a Fermi liquid. And so to connect with what John talked about in holography, this C Fermi surface is the gauge invariant fermion that you're measuring in whose Green's function that holography is measuring. And the F Fermi surface so far has not appeared really. It's hidden past the horizon. And from my perspective, really the key thing we need to understand from holography is what's going on with this F Fermi surface. Where is it? Can you tease it out? Because it's the n squared part that's controlling everything. That's really the key issue that needs to be addressed from my perspective. Yeah.
In the state you were just describing, sorry, remedial question. What can I think about the state you were just describing as a state of the C's and a state of the, which one is the hidden one? The state of the F's and a state of the B.
Yeah.
Which is
Sorry?
projected onto the right occupancy to give them a state of the electrons.
Yes, I mean, you can just view it as a phase of this theory.
What is the state of the B's that you're studying?
The B's are if the B Green's function is gapped.
Just an instance.
Well, I don't know. The B's, all the B's, you added some B's. There's some number of B's, and the B's have all formed a molecule. They've attracted an F, and those F's are now forming a Fermi surface. See, bosons left to themselves will Bose condense. The only way you can avoid Bose condensation of bosons is some non-perturbative process. Either the B's can fractionalize into many fermions, or the B's can bind the fermion and form another fermion.
So they interact with each other.
Then they form a solid. No one knows of what else to do with both. I don't know of anything else they can do.
You're thinking about a continuum state.
It doesn't matter. In the lattice, true. Okay, in some cases where you have integer number, then the solid is trivial. But yeah, so the B Green's function is gapped. The only gapless Green's function are the C and the F's. But this is one state, so normally if you just boson by themselves, if the bosons are gapped, you immediately conclude the bosons have to have zero density or some integer number if you're on a lattice. Here, this is a state where the bosons can have any density you want, because even though they're gapped, because they've actually transmuted into fermions by capturing an F fermion. Okay.
So here you are assuming number of fermions rather than number of bosons?
Yes, correct. So, and this kind of state, okay, again, this will take me far afield, is very natural in Kondo lattice models, where the F fermions are the F band that form a spin liquid, and the C fermions are the conduction electrons that just form what's called a small Fermi surface. Okay, so the focus so far has been on the C fermions, and I want to turn the focus now on these F fermions, which is a much harder problem, but that's really what we have to address seriously in thinking about applications to condensed matter. All right, so that's then the end of my field theory discussion. Any further questions on that? I think both John and I have covered it from somewhat different perspectives, so hopefully, okay, the one thing I should have, this argument that I gave you for the simplicity of the Z equals 3/2, perhaps something you haven't seen before, and it's something I want to emphasize. Yeah.
Going to also tell us a little bit about how, say, supersymmetric field theories we know about, where they fall into that?
I don't think we know the answer to that. So of course we'd love to know, as you were studying, take M theory, which by itself is when you compactify it in S7, it's a 2+1 dimensional conformal field theory. So now you turn on a chemical potential that couples to one of the R charges of M theory. What is the ground state in the large N limit? I think that would be a wonderful question to have a firm answer to. And what I'm trying to do here is put some global sets of constraints on the set of answers you could obtain. Yeah.
About the simplicity of Z equals 3/2, I guess
Yeah.
it's worth emphasizing the assumption that you had a Maxwell term for the gauge term.
Even if you didn't, you would generate it under RG.
Sure, but there could be more singular terms. You could imagine some situation where there's, say, Chern-Simon's term.
Oh, a Chern-Simon. So I'm certainly excluding Chern-Simon's term. Yes. But other than that, singular terms don't come on their own. You have to tell me about what low energy physics induced them, and I'm assuming that I have all the low energy physics here. But yeah, but this term here, even if you didn't put it, this term would appear under some RG. Just reduce the cutoff a little bit. It will appear with some term proportional to the cutoff, and then it's convenient, in fact, to make the coefficient equal to 1, and then you see the whole thing is scale invariant, provided Z is 3/2. So the tree-level action, when you throw out this term, the whole action is scale invariant only for Z equals 3/2, which is a rather remarkable point. All right, so now let's turn to holography, which is what you've all been waiting for. And now you can attack me, since I am in shaky ground, but let's see. Okay. All right. So come back to the question that came up. So as I said earlier, we've worked so hard to do the vector large N limit. Us condensed matter theorists have beaten each other to death in working out the 1 over NF expansion, and we've understood many things, but we haven't understood everything. So let's go ahead whole hog and just do the matrix model. So here's the model that I would love to know the answer to, and I don't know the answer, but I'm going to propose some constraints. So take SUNC Yang-Mills gauge field and just couple it to a bunch of fermions which are in the adjoint representation. Okay. And then I add a non-zero chemical potential. By this I mean a chemical potential that couples to some conserved global charge. It doesn't couple to any of the SUN charges, but something else, typically an R charge in supersymmetric gauge theories or whatever. This easy to construct a global U1 like baryon number in your favorite gauge theory, and that's it. So you take fermions which are adjoint, so the matrix fermions, take the large NC limit. Okay. So this is of course a very, very difficult problem, but we know how to draw graphs, and we can try to draw graphs and see what happens. So we try to just evaluate a few leading order graphs, and one of the things you find immediately is that you get exactly the same kind of singularities we got in the vector model. So the overdamped photon with the Landau damping, and the fermion with the omega to the 2/3 self-energy. I haven't summed all the graphs and just evaluated some subset of the graphs. But one thing you immediately see is that there is no 1 over n here. So these fermion self-energy corrections, which are 1 over NF effects, are in fact part of the theory, even in the NC going to infinity limit. So this is very, very important, because this implies that all these worries that Sung-Sik Lee introduced on singularities due to infrared terms, I mean, those infrared singularities are still there, but they do not introduce additional powers of NC. So the NC counting is exactly the same as that of a 't Hooft. So in this theory, a 't Hooft's argument for the large NC limit also applies when the chemical potential is finite. So we just have to redo a 't Hooft's counting, and of course a 't Hooft argued that you have to sum all planar graphs. I'm still left with the difficulty of doing that. I don't know how to sum all the planar graphs, but at least I can hope that the counting of powers of 1 over NC is faithful, just as in a 't Hooft's original calculation. Whereas in the vector model, it's not faithful. That's the difference. So that's why this is superior in a way. It's a cleaner limit to study, but we hopefully get the same physics in the end. Okay, you can also see that in this limit that there is no pairing instability, although you cannot rule out a charge density wave instability. This is something we'll eventually be writing up. Okay. So of course, a 't Hooft made this beautiful observation a long time ago for ordinary QCD, and it wasn't until recently, in the last 10 years, that finally understood how to make that work. And the reason, in some sense, it was so difficult was that ordinary QCD at zero density is a gap theory. It's a confining theory. And confining theories were not very natural to holographic descriptions. What you want in holographic descriptions are gapless theories, something with some critical scale invariant structure. Now here, adding a chemical potential gives you that. It gives you a gapless theory, and so there's some hope that things may be in fact be easier here. Well, I don't know. So anyway, so what I'm going to present is a pure conjecture as to what the structure of this large NC limit would look like, just for some scaling arguments. Okay. Yes, that's a very strong claim, but let's see. Yeah.
Fermions are still non-relativistic, right?
It doesn't matter. It doesn't matter. So so if you have relativistic fermions, then you get a Dirac cone structure. And when you have a Fermi surface, it's sitting over here. Okay. If you have non-relativistic fermions, you have a Fermi surface that's sitting over here. So when you're near the Fermi surface, the fact that you have the Dirac cone way down there is not of any importance. So the fermions could be relativistic, non-relativistic. The important point is they have a finite density. That's really the key thing. All right, so here's John's famous picture of doing RG, so I'm going to use this picture. Really, I just learned a lot from this picture. I'm just going to use this picture to say something about this problem. All right. So if you do the RG with R, the emergent holographic direction, then to get CFTs, you demand that when you rescale the spatial coordinates x by a factor zeta, time by the same factor zeta, because it's a relativistic field theory, and the proper distance in the full space be invariant, then the unique solution of this rescaling transformation, as John has discussed, is precisely the ADS, in this case the ADS4 metric, if x is in 2 dimensions. But in general, here little d, this is different from John's notation. Little d is the number of spatial dimensions. In John's talks, little d was the number of space-time dimensions. Small request, please use capital D for the number of space-time dimensions. It gets very confusing otherwise. All right, so that's the usual argument. So let's generalize this argument by allowing for different types of exponents. So John has already introduced the idea of this dynamic exponent z. So we're going to rescale x by the factor zeta, t by the factor zeta to the z. So z is a dynamic exponent. But I'm going to ask for one new thing. There's really actually no fundamental reason why the proper distance in the holographic theory should be invariant. But I'm going to make it quote-unquote covariant. I'm going to allow for ds, the full proper distance in the emergent space, to also rescale by a factor theta over d. Now d is the number of spatial dimensions. Theta is a new exponent. And really this is the key actor in my whole story. So what is theta? That's really the key question. Well, it turns out you can answer that through some very general arguments. Let's first actually find a metric for which this is true. So it's not that's just a simple algebra problem. In some coordinate choice, this is what this metric looks like. R is the emergent holographic direction, and I've just chosen R, so the coefficient of dx is 1 over r. That's just a coordinate choice. You can take any other coordinate you want. Once you fix r that way, everything else is fixed by this requirement. And r itself has this particular transformation under the rescaling. Okay, this is a simple exercise in rescaling that I urge you to go through. Any questions? Everyone see where this came from? So I'm just imposing this very simple requirement, and you'll see why I need this theta. So this kind of metric for theta equals 0 is what's called the Lifshitz metric. But as we'll see, the Lifshitz metric is really too limited for our purposes. You need something more general. Yeah.
If that solves Einstein's equations?
It does. I won't discuss that today. It solves Einstein equations for certain dilatonic models. Okay. That will be in tomorrow. Yes.
Can you say that this is, I mean, if you take this metric with z not equal to 1,
Yeah.
there's a energy tensor which breaks Lorentz invariance. I mean,
Yes.
Lorentz invariance is not broken by a chemical potential temperature only, but there's another.
Well, you certainly expect Lorentz invariance to be broken because the chemical potential breaks Lorentz invariance.
Yeah, exactly. But this
Yes.
is another. So this is a different.
Well, so I have a theory with broken Lorentz invariance. Now I'm trying to predict the low energy structure of that theory. So I'm just taking some very general structure, which I'm not imposing Lorentz invariance as a necessary criteria.
Yeah. I understand, but I mean.
It's coming from the chemical potential. Now, a question which I think you may be asking is how does theta or z depend upon mu or any other parameter? At this point, I don't know.
Can be derived from a chemical potential.
So there is a simple model I can solve where you take Einstein's gravity with the dilaton, you add a finite chemical potential to that theory, you solve it, you will get, in fact, I didn't solve it, that was done by Kiritsis and Sandeep Trivedi and collaborators. You solve it and you will get this type of metric. Yeah.
Is this metric singular in any way?
Yes, it's singular in the IR, but I won't really discuss that. But we'll see. For the values we're interested in, there is one limit where it's not singular. But generally, it is singular in the IR, so you would expect further instabilities deep in the IR, which may or may not be a good thing depending on your perspective, of course. Yes?
Is there a spontaneous symmetry breaking of arrow symmetry?
No. There's only one symmetry in this problem, and that's the global U1. Everything else is fake. There's only one global symmetry. That's U1. The gauge is not a symmetry. It's just a parameterization of your ignorance of the theory. All right, so what is theta? All right, so to understand what theta is, we're going to compute the entropy, the thermal entropy. So how do we compute the thermal entropy? So here, I'm going to assume, as is the case in holography, that when you take the system and turn on a finite temperature, you're going to get a horizon somewhere in the IR, and that the entropy of that horizon is precisely the entropy of your boundary theory. Okay, so let's say the horizon is at R equals RH. So now the Bekenstein-Hagen formula tells us what the entropy of that horizon is. It's simply the area. Now here this is it's a black brane. It's infinite in this direction. So we're interested in the entropy density. Now recall in the metric I chose, you had dx over r. So every factor of dx gives me a factor of 1 over r. And so the entropy density is just RH to the power minus d. Okay? Everyone got that? That's just computing the area of the horizon. Okay, so that's RH to the minus d. Now we just put it together. We know how r scales, we know how time scales, and we know that time is an inverse temperature. So you just do all those scaling laws. Remember the scaling, remember that time is an inverse temperature. Put it all together, you find the entropy is T to the d minus theta over z. So that's the key result here. So what you see what theta is. You can now theta is the dimension deficit. Remember yesterday I talked about the Stefan Boltzmann law, or the hyperscaling prediction, that the entropy should be the spatial T to the d over z, where d is the number of spatial dimensions and z is the dynamic critical exponent. That's a very general statement of theories that obey hyperscaling, one of which are free photons, which has d equals 3 and z equals 1. But you expect that for any sort of critical theory. So here we find we don't get hyperscaling, we get violation of hyperscaling, and theta has the exponent, which has been known before in condensed matter physics in different contexts, which tells you how much hyperscaling is violated. So what it's really roughly saying is that the low energy degrees of freedom have a phase space which is not d, but d minus theta. That's the meaning of this deficit. And you really need that deficit in my picture of the Fermi surface that I've emphasized so far. All right, so that's what theta is. It's the hyperscaling violation exponent, and it's mostly not appeared in string theory computation so far, or not noticed, except these papers by Kuritzis and Trivedi et al. I'm arguing here that it's really something absolutely crucial for any discussion of compressible quantum phases on the boundary. So, all right, so you may recall yesterday I showed you that the entropy density, I should remind you. So from the field theory, which we discussed a while back, now where did it go? All right, I can't find it, sorry. So I just put it on the board. So we showed for the Fermi surface, non-Fermi liquid, the entropy went as T to the 1 over z. And the reason for this 1 over z was simply the fact that there was just a one-dimensional phase space of excitations transverse to the Fermi surface. So that brings me to the main claim that anytime you have a non-Fermi liquid Fermi surface, the emphasis on non-Fermi liquid is actually important, that d effective should be 1, and so theta must be d minus 1. So you see this is highly non-trivial for any d greater than 1. And d equals 1, theta is 0, and in fact z is 1, and so you're all done. But then this is my claim dual of this large NC limit of the adjoint fermion gauge theory, that it's described by this metric with theta equals d minus 1. And this constraint on theta just comes from the requirement that the entropy be right, and the entropy be quasi one-dimensional. Yes?
Unfortunately, in your analysis, that Z is not 1.
Next step, just wait. So here, of course, I mean, there's a strong version of the statement. The strong version of the statement is that any compressible state, which is not a Fermi liquid, which has hidden Fermi surfaces of gauge charged fermions, must have theta equal to d minus 1. The weaker version is that a compressible state of fermions coupled to gauge fields must have theta equal to d minus 1. An even weaker version, this is all wrong, but okay. I tend to believe the very first statement. Okay.
This means the ADS rising Nordstrom black hole does not have a.
No, that has theta equals infinity or something like that. Yeah. So that already we knew, because in the ADS rising Nordstrom black hole, Z is infinity, so T is yeah. Okay. So there's some limit of theta going to infinity and Z going to infinity. That corresponds to it. Yeah, you have to look at the entanglement entropy to really fix theta for ADS rising Nordstrom black hole, which I'm going to do in a minute. But you already had violation of the Nernst law. This is certainly perfectly consistent with the Nernst law of thermodynamics, and so would theta equals d minus 1. Yeah.
You've given the metric here, but do I need to know what fields live on that space?
I certainly do. So this is the first step. I absolutely do. And I'll say a little more about that tomorrow, maybe. But right now, we're just I'm just applying what I learned from John. I saw this picture and started working with it. All right, so what about Z? Okay, now there's another beautiful argument here, originally made in a slightly different language by Takenagi and collaborators, which is, here you've got a metric, and let's assume it's a solution of some theory of gravity, where at least the gravitational action is just the Einstein action. Then, knowing the metric, you know the stress energy tensor. Then there's a constraint called the null energy condition, which is apparently very, very crucial in all classical computation of gravity. So you apply the null energy condition to this metric, and you come up with this inequality. So theta must be d minus 1, and Z must be greater than or equal to 1 plus theta over d. Another crucial structure of this whole theory. So the whole gravitational theory won't make sense unless this is true. Now, for d equals 1, theta 0, Z is greater than or equal to 1. Well, d equals 1, probably Z is just 1. So the one-dimensional case, this works. I mean, in 1D, when you have finite density fermions, it's still a CFT because you just shift along to the Fermi points. But the most amazing thing to me is that if you put d equals 2, you get theta equals 1, then you get Z is greater than or equal to 3/2. So that's really quite remarkable. So the Z equals 3/2 that I showed you from this consideration of the Fermi surface coupled to a gauge field and the scaling argument there, that is nothing whatsoever as one can. It seems to be completely disconnected from this null energy condition of gravity. But you get the lower bound to be precisely the value that you obtain in field theory. Okay, this could be just an accident, but accidents like this haven't happened too often in my life, so I'm certainly excited. Okay. There's also, somebody asked about singular, so there's a paper by Shagulian who showed that if you take the general class of metric, that only precisely for Z equals 3/2, the tidal force is not infinite in the IR. So there may be some reason for believing that only the lower bound ultimately is a stable, but that still remains to be seen.
What happens for d equals 3?
So d equals 3, you get Z greater than or equal to 5/3. Now, from the field theory side in d equals 3, we don't have any reasonable field theory which is strongly coupled. You just get this omega log omega, and in fact, people call it a marginal Fermi liquid, but there the gauge coupling is actually irrelevant. In other words, the one loop answer is the exact answer, period, as far as the singular term is concerned. So in d equals 3, from field theory, we don't have any examples of strongly coupled non-Fermi liquids. This suggests that there may be one that only holography will tell you about, where Z is equal to 5/3 in that case. We don't know how to make that. That's another interesting problem.
With When this inequality is saturated, does that mean what does that mean for the stress tensor of the gravity construction? That's how much the no energy condition is saturated.
Yeah, I'm not. I think it has some form. I'm not an expert on that. Right.
It doesn't lead to some simplification.
So the dilaton, we realize this in a dilatonic theory, the dilaton doesn't flow off to infinity in the IR for z equals to 3 halves, but the solution still seems to work. So there may be, I've been talking to various people who have been mentioning that precisely for these values there's some extra symmetry. This metric seems to be related to something called Kastner universes, but at this point it's well beyond my pay grade. But I'm hoping people will certainly study this for various values of z and theta. Okay, so that's one exclamation mark. So this is something to get excited about, and just by matching the entropy density, we seem to have gotten this 3 halves number at least popping out as an inequality anyway. Yeah.
What happens if d is equal to theta? So the effective number of dimension.
Yeah, so that's not a case so you find lots of problems in that case. One of them having to do with the entanglement entropy. So the entanglement entropy has something which is just the next topic, has something called the area law, and that area law is violated when theta is greater than d minus 1. So in fact, more generally you can argue that theta must be always less than or equal to d minus 1. Okay, so now so we've got a metric. What else can we do with it? When you have a metric in holography, you can compute entropy, and to do anything else seems like a lot of work. But there's one more thing which we've learned in the last few years. You can also compute another entropy called the entanglement entropy. So this is a quantity that characterizes the ground state of some complicated many-body system. So here's my boundary theory sitting in some plane, has two regions A and B, and the entanglement entropy is just the von Neumann entropy of the reduced density matrix of region A. I guess Srednicki was one who introduced this quantity. You take the ground state wave function, you take the trace over the B degrees of freedom. So this is just a pure state rho. You trace over B, you get a mixed state characterized by the density matrix rho sub A, and then you compute its von Neumann entropy, and that's the entanglement entropy. Okay. So this is quite a difficult quantity to compute from field theory, but some progress has been made. But what we've learned in the last few years from the Ryu-Takenagi formula, that it's actually very simple to compute using holography. But let me just say a few things about field theory. So one result that has been done is to compute the entanglement entropy of a Fermi surface. So take free electrons and compute its entanglement entropy. That itself turns out to be quite complicated, but it can be done. And in 2 dimensions, the answers of this form. It's for a circular Fermi surface, it's 1/12 kf. Kf is the Fermi wave vector times p, which is the perimeter of the real space boundary between A and B. So this boundary can have any shape you want, but you just exactly the perimeter times log of kfp, and that's the universal answer. It's also believed to hold for a Landau Fermi liquid exactly with no further corrections. So this is this is a violation of the area law. So the area law in this case would say that the entanglement entropy between A and B should be proportional to the perimeter. That's the area law, which we believe holds for most local quantum systems. But there are occasional violations of the area law. In particular, conformal field theories in 1+1 dimensions violate the area law with a log term, and Fermi liquids in any dimension also violate the area law with the log term. So this log term is a violation, but it's a mild violation of the area law, only logarithmic. And this is, in fact, I think, proven in any dimension for a Fermi liquid, that this is what you get. Right, okay.
Can you say a little bit why this seems to be so independent of what theory you computed in?
It's not in general, for a Fermi liquid it is. Oh yeah, the point is, of course, one way to understand it, this is what I was going to say. You can think of the Fermi liquid as just a bunch of one-dimensional fermions on the Fermi surface, one for every direction. And you could pretty much get this answer by just taking the naive picture and adding up the different directions. It's a little bit more complicated to get the prefactor exactly right, But this 1/12 is closely connected to the 1/6 you get in 1D CFTs. C over 6 log L is Cartesian result for any CFT 1 plus 1. Or no, sorry, we'll check in class. We just did it before. That C over 6 is related to this 1/12 here. So it's descends from the 1D nature of Fermi liquid. Okay, what about the non-Fermi liquid I talked about so far, which is the Fermi surface coupled to a gauge field? Well, there is so far really only a numerical study of that by Zhang et al. Recently. And numerically anyway, they seem pretty confident that you get the same P log P behavior. Okay. All right, so that's the review of field theory. So now and it's still something in progress. Now let's do holography. So holography, I want to compute the entanglement of region A with its environment. And this is the emergent holographic direction. So there's, as I said, a famous and very beautiful result of Ryu and Takenagi, which initially started out as a conjecture, but at this point it's been checked in many cases. So people are quite certain that, well, I shouldn't say certain, it's not certain, but there's overwhelming evidence of supporting it. And their proposal was the following, that in this holographic space, you extend the boundary of region A to a surface, and the minimal proper area of that surface is equal to the entanglement entropy. So, I mean, they were inspired by the Hawking entropy formula, and you also use some constraints on the subadditivity of the entropy. But anyway, this is the result that they came up with. So it's a beautiful result because it's remarkably general, but it's also very beautiful because now a computation of entanglement entropy is very simple. If you have a metric, turn the crank, compute an area, minimize it, you're done. And something that we had a lot of fun doing. So what they showed, for example, that this formula agrees perfectly in one dimension. It gives you the area law for conformal field theories in 2 and higher dimensions. It even gives you corrections to the area law, subleading corrections for conformal field theories in higher dimensions, and so on and so forth. And so now we have the tool, since we have a metric, to compute it for this non-Fermi liquid. Okay, all right. So here's the metric with theta equals d minus 1. And so let's take this metric and compute the entanglement entropy by the Ryu-Takenagi formula. So this is what was done by Ogawa et al. And so now there's 2 exclamation marks. I'm getting more excited. So for precisely this value of theta, you find the log violation of area law. So this is another check. It's an independent check because for ADS2 metric here you'll find a volume law for ADS2. But the area law, okay, I think, except in maybe possibly in some supersymmetric models with additional ground state degeneracies, it's hard to believe how you're going to violate the area law in any local quantum field theory. But okay, maybe string theory is going to give us examples of reasonable systems that violate the area law, but so far that would be a very strong claim. But here, we didn't put anything by hand. We just had this metric. I argued for this value of theta, and yes, you get exactly the area law. But even more, there's another result I mentioned here, which is for a Fermi liquid, that this P log P form is independent of the shape of region A, provided it's big enough. Doesn't matter what shape you take, it can't have corners as long as it's smooth. Then you always get P log P, where P is exactly the perimeter. So that's a geometric statement. It's not true for conformal field theories. For conformal field theories, the correction to the area law depends on the shape. It depends on all kinds of geometric properties of your manifold. As you know, for many other things about conformal field theories. But for this theory, in fact, it doesn't depend on the shape. So that was our first attempt to extend this result of Ogawa et al. We looked at it for all kinds of shapes. And we found, yes, indeed, this is also true holographically. It's exactly P log P, and that the coefficient of P doesn't change as you change the shape of the region, provided you preserve its perimeter. And so that's 3 exclamation marks. So at this point, I'm, of course, trying to contain my excitement. Yes.
These dilatonic constructions you made.
Yeah.
Was there anything special about these values of theta and z?
No. So that's, I'm actually going to finish early, but that was the next topic, but I haven't prepared my slides. So certainly, I think you're onto something. I mean, can you, so far from the dilatonic side, from the gravity side, there's nothing special about theta and z in any values, although in all of the dilatonic constructions, you certainly absolutely do satisfy this inequality, which you should.
And all the dilatonic constructions are supposed to be legal solutions of string theory.
The legal solutions of classical gravity. I don't know about string theory.
They descend from some supergravity.
Yeah, but theta and z will depend on the parameters in that supergravity action. So
Yes.
you will get some answer. Not, of course, there could be many supergravity actions. But
Oh, so the calculations are done in some, you just write down a supergravity.
right, it's like a next
Okay,
dimension.
yes.
Yeah.
Okay,
Yeah.
logical.
Well, it's not even supergravity. It's Einstein gravity with a dilaton with some potential and some coupling.
I see, but not starting from a consistent supergravity.
Maybe some people have, but the papers I've been reading don't.
Okay.
I think that's certainly you're putting a finger on something we really need to sort out, which is, I think, the next step is can you, from more top-down arguments, get these values? I mean, I'm going the other way. I'm saying, okay, from what I know about field theory, these are my very important constraints. And anything that doesn't obey these is a radical departure from what we know in field theory. Yeah.
One thing you can show in these dilatonic constructions is that many of the scalings that appear there you can explain by using dimension reduction techniques. And in particular, this reduced dimensionality of space that
Yes.
you were mentioning,
Yeah.
you can show that what this tells you is that it's exactly equal to the number of spatial dimensions that you would get in the uplifted picture.
Yeah, well, those arguments were made, as far as I know, for theories at zero density.
Actually, with Ilias, we made them at
Sorry?
finite charge density.
Sorry, who?
In the paper with Ilias,
Yes.
we made them at finite charge density.
You did the compactification. So where does the charge density live? It lives on the boundary theory, but the compact dimensions have no charge.
Exactly the construction that you're talking about, that is the Einstein-Maxwell dilaton.
Okay, all right. Yes.
And so then you, as you were saying, there's some reduced dimensionality, this df that
Yeah.
you're mentioning. So if you translate this in the higher dimensional dictionary,
Yeah.
then this df is exactly the number of spatial dimensions in the uplifted theory. So that tells you that in the lower dimensional theory, actually, it sees all the higher dimensions.
I see. So this means that so if theta should be 1 for d equals 2, so you have to compactify from, I don't know, 86 or something. I don't know. Okay.
This dimension reduction thing,
Yeah.
It's a tool to explain.
But again, from
how
those
the
methods,
other way they
you
are.
can still get a large number of values of theta.
Sure.
Yeah. So I'm saying, okay, I think you could for theories of zero charge, but the conjecture is that if you have a system which is compressible, has a finite charge density, then this is the only value of theta that's consistent in the end.
Right.
That's the strong
I'm
claim.
not,
Yes.
testing this in any way.
I have, that's something I'd love to be proven wrong on, but my bias from field theory indicates that claim. Anyway, yes.
Didn't you tell me that this is the only values that renders the solution singular? Sorry, non-singular. Right?
That's an additional fact that I certainly didn't know of when we were working on this, and then Shagulian pointed this out, which
That's a
is
good justification. I mean,
well, okay,
why
it's enough to get excited. Yes.
Well, in the construction, you still have the true curvature singularity.
Sorry.
even these ones have
Yes.
a curvature
What
singularity.
Julian is saying is that the tidal forces that an observer would feel going through the horizon
what about the
are not
curvature
infinite
singularity?
in that case.
What about curvature singularities?
There is always a curvature singularity
Yeah.
sitting at the
Ah,
center.
that's bad. That's very
Well, okay. There are other reasons for believing that I mentioned earlier that the large end limit on the field theory side for adjoint fermions always has a charge density wave instability. So I'm working on this with David Wake and Max Metlitsky. So maybe there is eventually some instability here also. It's possible.
Then again, if you have dimensional reduction in mind, then even if there's a curvature singularity, it might not be so bad because this can be resolved again in the higher dimensional picture.
And is it resolved or it can be?
Well,
resolved?
you can show that there's a large chunk of the theories that uplift to Lifshitz solutions. So there you have no curvature singularity, you only have the tidal one.
But you have the tidal forces.
So,
well,
So clearly there's much more work to be done. Yes.
Finite temperature resolves this.
sure. You can certainly do that.
You
But
can also put finite temperature.
yeah.
So it's not so bad.
But I think this question of resolving the singularity and what energy scale that singularity gets resolved is precisely the key question for answering what is TC or something like that in some semi-realistic model.
Is there some meaning to the fact that with theta equals d minus 1, that the line element scales linearly with scaling, no matter what the dimension? Because the line element
Yes.
scaled is d minus theta.
Well, so that's connected precisely to this fact that when you have a Fermi surface, the fermions disperse only in one direction.
I see.
Yeah, so that's where it came from.
Yeah, I see.
Okay, so that your phase space of low energy excitations is one dimensional. That seems to be the key property of a Fermi. That's the only key property of Fermi liquid we're using. So at least the way I present it, that's the only property I use. And then you could take the rest of the computation, which builds on the work of Ogawa et al., as a way of computing the entanglement entropy and seeing all kinds of other things work out correctly. Yeah.
Blaze's comment was actually, he was suggesting that there's an interpretation from the higher dimensions of what these.
Yeah, I've seen those papers. I admit I don't understand them because my weakness in string theory. But anyway.
But it's interesting that in that case, those dimensions have the topology of a torus, and I think they're just is that right? They're just circles, like products of circles. The extra dimensions that we're counting with theta.
It's a question for you, but
I think that's right.
I can't hear it. Sorry.
so he's asking whether the extra dimensions that you fold up on are just toruses or spheres or
Well,
what.
in the the paper we did, yes, we're just looking at the simplest compactifications. That is, for instance, a diagonal compactification along a torus or along a sphere. Then I'm sure you can think of more complicated constructions that would give other results.
But it suggests that maybe we should be careful about saying that this is the gravity dual of this particular non-Fermi liquid state that you're studying, since the
Yeah.
geometry of the low energy excitations is something that should be real. I mean, something that's visible.
Well, okay, maybe yes.
There could be other ways to realize this.
Sure. But all right, the statement that I'll still try to hang on to is if you have a non-Fermi liquid which is compressible and with a hidden Fermi surface, that the gravity dual has some IR sector which is described by this metric. This is not by no means a specification of the full gravity theory. This is a constraint on the IR sector of that theory. And really that's all you need for the arguments on the entropy and for the entanglement entropy. Okay, so these two features of the entanglement entropy all work out right. So we got three things for free from our assumption. We took that as an input, and we got z greater than or equal to 3/2. We got the log violation, and we got the shape independence. They all come out correctly. So there's now one more thing. I guess I haven't timed myself properly. I'm going to finish early, but time for plenty of questions, which I'll discuss tomorrow. I don't have the slides for it. For that, you really need to address this dilatonic theory more. You need a microscopic model. So what I want to know now is how does all of this, how the parameters as coefficients here, how do they depend on the charge density? Okay, and the reason I want to know about that is that the entanglement entropy does depend on the charge density by this factor of Kf. So remember I mentioned Luttinger's theorem. Luttinger's theorem tells you that the area enclosed by the Fermi surface in a Fermi liquid or a non-Fermi liquid is equal to the total charge density. So if you give me the charge density, I know Kf. That's the geometric calculation. So once I know Kf, I know the entanglement entropy. So in this theory, I've computed holographically the entanglement entropy. But I'd like to know how the entanglement entropy depends on the charge. And if all of this is to hang together, it should depend on the charge just in exactly that way. It should be proportional to Kf and not on anything else. So the coefficient, you would say the coefficient of this is some UV number. In the calculation John was doing, Kf, something determined by the UV physics. But we know that it's not that arbitrary. It depends only on one particular detail of the UV physics. That's the charge. So here we have a way of computing Kf of this hidden Fermi surface, which is to figure out what the coefficient of this P log P term is. and to see whether it depends on charge in exactly the right way, and also to see that it's universal, that is otherwise independent of all the UV details. And it turns out, again, quite remarkably, through a variation of this attractor mechanism of horizons, we find that's exactly what happens here, and that's what I'll say a little bit about tomorrow. That the coefficient is precisely Kf and is independent of all UV details. So that's the 4 exclamation comments that I'm going to make tomorrow. But I should have prepared it, but sorry, I have enough time to go through it, but I don't have the slides for it. Yeah, and I'm not done. I'm just going to summarize then. So we'll have an early lunch. Okay, so then summary. So this is what the problem I'm talking about. More very generally, you take any infinite continuum translation invariant quantum system with a globally conserved U1 charge Q, and for now, spatial dimension d greater than 1, and I want to classify and understand something about 0 temperature phases with dq d mu not equal to 0. So we attack this problem by 2 routes. One is the field theory route, and I talked about in 2 dimensions how you get this very unusual non-Fermi liquid state with z equals 3/2, and entropy going as t to the 1 over z. Then today I talked about, well, let's address the same problem holographically, where I put in these constraints that the entropy should go as t to the 1 over z. And then I found that you had to introduce this new exponent theta, and theta had to be d minus 1. So to summarize, in the field theory side, we had a gauge-dependent Fermi surface of overdamped gapless fermions. And here the Fermi surface was gauge charged, so it's hidden to observables on the boundary, at least the Green's functions, on the simple Green's functions you can compute. So we put the constraint that entropy is t to the 1 over z, and on the holography side, we found this worked provided theta was d minus 1. Then we know on the field theory side that you have entanglement entropy, which has log violation and independent of its shape, and remarkably, you get exactly the same thing here. Only for this value of theta. For any other value of theta, you do not get the log violation. And finally, and in some ways most remarkably, this value of z that came about from 3 loops in t equals 2 is the same, and also of course appears in the very simple scaling argument, but isn't verified to 3 loops. Appears as an inequality from the non-energy condition in the theory of gravity. So to summarize, this is kind of the kind of pictures that I borrowed from John and Sean. Drawing this picture, so you have some boundary theory with some charge q, and the state I've been talking about, this non-Fermi liquid state, is in which this charge q then is dual to some electric field in the bulk, and that electric field just goes all the way out to the IR. So that's the non-Fermi liquid state. There are no fermions in it. It's a bosonized description. The fermions, we have been able to banish them because we're only focusing on gauge invariant quantities. And there are no gauge invariant fermions in the simplest version of this theory. So I'll explain this a bit more tomorrow. I think John also mentioned it briefly. There turns out to be a deep connection between the Luttinger theorem on the Fermi surface and Gauss's law on how the electric field goes through the bulk here. Well, in this case, it's kind of trivial because the electric flux here must equal the electric flux there, and that's precisely what leads to our results on the determining Kf through the entanglement entropy. But the kind of calculation that John mentioned is when you put in some boundary fermions, which in this case correspond to gauge invariant fermions, and in the electron star approximation, you get some finite fermion density in the bulk. So then this kind of state is what this FL star state is, where you've got total charge density. Part of it is eaten up by the fermions sitting in the bulk. Those are the gauge neutral fermions, which form a small Fermi surface of order 1. And so John was investigating this part of the fermions for a variety of background metrics. But they don't eat up all the flux. In fact, in the large N limit, most of the flux keeps going. And there's still some hidden Fermi surface in there. And we really, the objective here has been to really say more about that. And the more you can say, the better. And finally, in the Fermi liquid, what John mentioned is where really the entire flux is eaten up by the fermions. And at least in my simple calculation, we expected the geometry to terminate. But John showed that there are actually beautiful solutions where it doesn't terminate, but still all the flux is eaten up by the fermions in the bulk. So not quite so that's a Fermi liquid, at least this way when it terminates. In John's calculation, it's a Fermi liquid at n equals infinity, but I expect it to have some non-Fermi liquid effects at higher orders than 1 over n. And my guess is that his solution is really correspond to some quantum critical point between these three phases that I've been discussing. But these are all things that need to be sorted out. So that's the end of my talk.
So we have plenty of time for questions.
You sort of worded stated a conjecture that a particular field theory, this
yes,
three-dimensional field theory, had this gravity.
2 plus 1 dimension. Yes.
This one-dimensional field theory had a gravity dual description. I want to understand how seriously you meant this conjecture, in the sense of, do you really mean gravity, or would you be happy with a string theory with many of the same symmetries, or do you want really a two-derivative gravity dualism?
Okay, let me tell you all of string theory that I know. No, okay. So, I might at this very naive level. So I just read a Tufts paper from 1970 something, where he has the planar graph expansion, and he argues that that means that there's some genus expansion of Feynman graphs. So what we can show is that for this particular theory, that all of those statements in the first half of a Tufts paper are still true, which is fairly non-trivial. It's taken a while to realize it, but that is still true. So then, after that, everything else I don't mean very seriously. I'm just learning what I've learned from string theorists, that once you have a planar graph expansion, there probably is a weakly coupled gravity dual.
Weakly coupled string dual.
Okay, well, I'm corrected there. Explain it to me.
Let me make that more.
Okay.
If you take a theory with adjoint matter.
Yes.
And you try to count how the number of operators in the theory grows with dimension.
Yes, yeah.
On very general grounds, if the theory is weakly coupled or not very strongly coupled, the number of operators grows exponentially.
Okay.
Just because if you've got a trace and you've got k units, in each of the slots you can put, if you've got m operators, m choices here, that's m to the power k.
Right.
Okay. Now, this exponential growth is a hallmark of having string theory.
Yes.
It's the exponential growth of stringy states.
Right.
Okay. In the gravity limit, however, something really special happens. Right. Most of these exponentially many states go off to infinity.
Yes. Okay.
And only a very few are left.
Yeah.
And that gives you gravity.
Okay.
So I was wondering whether you expected this to be true of your theory.
I don't know that. I mean, partly to answer this question is why we've been studying this 1D case. I think. So the naive understanding from the field theory is that, roughly speaking, each direction of the Fermi surface is our large n. That's what Sunset's calculation shows very beautifully. That if you really think of each direction of the Fermi surface as one component of your matrix, so now the question is, I guess, if I take multi-trace operators around different directions, well, most of them just factorize. They're not primary operators. So there's only a few primary operators at antipodal points. So it's possible that there's a gap, but I agree that we don't know. That's a good point.
There's another question.
Quick question. So you mentioned that this green stuff in the bulk is the Fermi surface is made up by the probe field that we put.
Correct. Yeah.
But we don't actually know what's behind the horizon because we don't know what the background of the boundary theory is. So why is it still legitimate to call it a Fermi surface, or do we even know it is a Fermi surface?
Absolutely. You're asking exactly the right question. So we don't know what's behind the horizon. So how do we figure out what's there from the boundary? So we can measure the entropy. So that's what I did. Measure the entropy and said, oh, it looks like a Fermi surface. And we measure the entanglement entropy. It's shape independent. It has log violations. More evidence that there's a Fermi surface. So is that the end of, is that conclusive? No, even I'll admit it's not conclusive. I think what would be conclusive is measurement of some correlation function that oscillates. Okay, so now if I have a gauge-dependent Fermi surface, suppose I have a non-Fermi liquid. So this is my non-Fermi liquid. So I can't compute the 2 Fourier-Green's function because that's gauge-dependent. But suppose I define a charge density, rho of r, which is psi dagger psi. This is certainly gauge invariant. So now if I compute rho of r, rho of 0, then in general scale invariant theory, this would be r to some power, r to the alpha. Okay. But if you have a Fermi surface, you get low energy processes where you scatter from here to there. Okay, and the diameter of the Fermi surface is 2kF. So what you will get then are cosine 2kFr over r to some beta. Okay, so if you saw something like this, I think that would be conclusive evidence for a Fermi surface past the horizon. So I would love to see somebody do a stringy calculation of fluctuations about this kind of larger limit where you see this. I think that would seal the deal. So short of that, everything else seems to work. Now this exponent beta then will be related to a certain high momentum operator. So it's in fact not true that there aren't high momentum operators in this theory. They're just not present in the leading field theory. They're not that important, but they're there. There are high momentum operators at 2kF. There are high momentum operators, any momentum you want. They're just composites. There's a high momentum operator whose exponent, whose scaling dimension is going to compute this determined beta. So to me, that's one of the key outstanding things that needs to be established.
So you're saying that you expect beta to be
anomalous. So
n squared?
Huh?
Are you saying that the exponent is somehow of order?
I don't know how big, so I don't know. So, but what probably is the case is the prefactor of 1 over n squared here, which is why you're not seeing it so far.
But based on your picture of from the field theory, isn't that the coefficient parametrically the same order as the?
Well, I only know how to do that. I do not know how to compute that in the matrix large n limit. We don't know. Okay, in the vector large n, you can compute that exponent, and probably even the coefficient we have trouble with, since we don't know what the large n limit exists. So we don't know. So that's another thing. Perhaps some exact solution in 1D might settle is what is the prefactor and where is that term. But it has to be there. I mean, there's no question it's there in any kind of non-Fermi liquid state. So there's certainly so I should have mentioned these are the analogs of Friedel oscillations. So the Friedel oscillations, which survive even in a non-Fermi liquid, except for Friedel, this beta was something trivial like 3 or 2, depending on the space dimension. But here it could be a non-trivial exponent. So a non-Fermi liquid should have Friedel oscillations. And if you could see them, that would tell you about the Fermi surface that's hiding. So certainly I'm conjecturing, I've gone out on a limb here, this will happen. Okay. And if it doesn't happen, you would have learned about a new phase that condensed matter physicists know nothing about.
For your vector model, because the number of flavors is very large, sometimes your QED should go to IR free, even though you want to start with infinite coupling.
No, that's only for zero chemical potential. So all those arguments for large vector models QED for zero, that's perfect. So the ordinary 1 over NF expansion works beautifully and correctly at zero chemical potential. In fact, it agrees with supersymmetry, as we showed in a recent paper with Pufu and Klebanov. There's no problem with the vector 1 over NF expansion. But there is a problem with the 1 over NF expansion at finite chemical potential. That's
maybe
crucial.
because you start with infinite coupling. Maybe you have to have a coupling scale divided by mass should play some role there. Then maybe it's working.
I don't think so. I think that is a problem we condensed matter physicists have understood. I think we've got that straight. Yeah, sure.
You had a metric which almost had an isometry, but not quite, because it scaled with an overall.
Yes, there was some technical word for it. Andy Strummer told me it's some
conformal isometry.
No, it's some tactic or something. I don't know. Whatever. Okay.
I wanted to ask whether having such a metric, an almost symmetry can be detected on the field theory side. It's not a symmetry on the field theory side, it's not an isometry. So what is it?
No, it could be a symmetry. That depends on the action, right?
No, I mean the field theory obviously has that. It's the fact that okay, yes, there is a symmetry.
The oxidized one could have a symmetry.
No, so let me come back to it. So this is the picture I got to show you. Yeah. So here, when I considered the low energy theory, I picked a point. Okay, and then I wrote down a two-dimensional field theory sitting at this point. Okay. Now, suppose I had a point P here, I want the Fermion-Green function. So in this case, I would just compute it for this field here. On the other hand, I could equally have taken a point over there and still computed the same Fermion-Green function. So there's a symmetry, kind of a sliding symmetry, which is related to the Galilean invariance of this d by dx minus d by dy squared, which actually imposes that it doesn't matter which theory you take. That is, there's really an infinite set of 2 plus 1 dimensional field theories, but they sew together consistently because of the sliding Galilean invariance. I think that's the symmetry. So one of the consequences of that symmetry is also the violation of hyperscaling. That you look at this theory, this theory also looks 2 plus 1 dimensional, but because of the sliding symmetry, its entropy only goes as t to the 1 over z. And you get an overall factor, which is the length of the Fermi surface multiplying the prefactor. So I think that's the symmetry.
And do we have any further questions? Well, let me just say one more thing before we thank him. So for the Gong Show speakers, please make sure that we get the talks. So just give them to us on a memory stick or whatever. So let's thank Subir again for this.